Hi guys, so in this video we're going to go over drawing a titration curve and understanding what the titration curve is doing for an amino acid that has 3 pKa's, right? So it has 3 hydrogens or 3 protons that it's donating. All amino acids have at least 2 because they have this carboxy group up here and this amino group down here, but some actually have R groups which contain functional groups that can donate protons. So in this case, lysine, which has this R group at the end, can actually donate that proton, so that gives it a third pKa value. A third pKa value. Okay, so first, let's go ahead and draw out what our pKa's are doing. Okay, so essentially what the actual acids and conjugate bases are, then acids again, conjugate base. And a lot of these are actually amphoteric, right? These two in particular are actually amphoteric, and what amphoteric means is they can act as amphoteric, which means they could act as acids or bases, right? And that's kind of key here to understanding how these are backward and forward reactions in both cases, okay? So let's go ahead and just conceptually first understand what's going on. Let me just fix this real quick. I'll be right back. There we go. Okay, so first let's draw in what these next 4 steps are going to be. So from here, our first pK is when we lose our first proton. And which proton is it going to be? Is it going to be our carboxy group, our amino group, or our R group amino group? It's going to be our carboxyl group. The carboxy group always donates the proton first. It is the most acidic of these 3 functional groups. Right, so what's going to happen? If we donate that, you're still going to have an NH3 here, plus charge. But now we're going to have a COO minus because we gave up that proton. And over here we're going to still have an NH3 plus. So let's also draw in the formal charges. What's our formal charge for this entire molecule over here? It's a +2. What's our formal charge for this entire molecule here? Well, we have +1, +1, -1, so we have a +1 formal charge. Now what's the second proton to go? Is it this proton or is it this proton? It's going to be this amino proton. That's the one that's the most acidic. This R group is a bit more stable than this one. That goes for all amino acids, by the way. The first proton to leave is going to be the carboxy group. The second proton to leave is going to be the amino group, and the third proton is going to be the one in the R group. And also keep in mind, not all amino acids have this third pKa. Some only have 2. Okay, so our next step is going to be deprotonating this one. So we still have the COO minus over here, and this NH3 is now going to become an NH2. And it's going to be neutral, right? It has no charge. And this NH3, again, hasn't changed yet. So it's still an NH3, and we have a charge of 0 over here. Let me actually draw these charges in a different color. Let me draw this as +2, +1, 0. And also that was a pK of 3 of 10. That's the pKa. And then let's go ahead and draw what happens in our last step. So again, COO minus hasn't changed. We have this NH2, which is still neutral. And now we donate this last proton in this NH3, and now we have an NH2 here. So now we have a formal charge of -1, right? We only have 1 charge there. So our formal charge is going to be -1 over here. Okay? So we can see what's going on here generally. We can, also kind of figure out what our isoelectric point is and all that. But for now, let's just say we've done our job, understanding what's happening at each of the pKa's. Okay. So now let's go ahead and start thinking about how we're going to draw in this titration curve. So let's first understand what happens what do titration curves look like in general, right? So we're expecting something along the lines of this, right? 1 equivalence point, 2 equivalence point, and then 3rd equivalence point, right? So something's going to look pretty close to this is what we're going for right now. So let's first draw in what we already know. I drew my x-axis in terms of equivalence, right? So we know our first equivalence point is going to be somewhere on this vertical axis right here. Our first is going to be somewhere here. Our second is going to be somewhere here. And our third is going to be somewhere here. And again, the inflection points on equivalence points always look like this, right? So it always looks like it's doing this. this. So these vertical lines will do for now. Okay, so I'm going to draw our line in red. What pHs do we even know that we can mark? Well, we don't know what the equivalence points are, and I'm not telling you in this problem. There's no indication of what the pH equivalence points are. But let's try to figure out as a general rough sketch. What pH points can we figure out? Well, we know that the halfway point between equivalence points, so between 0 and 1, so over here, between 1 and 2, and between 2 and 3 is right here. We know these are where the pH is equal to the pKa, where we have an equal amount of our conjugate acid, well, not our conjugate acid, our acid and our conjugate base. And that's in the realm of this, in this scope. If I zoom in, if I scroll over a little bit, in this next pKa, the acid is over here, right? These are all relative terms. And conjugate base is over here. And if I think about it in this scope, my acid is over here, and my conjugate base is over here, right? So that's one way to think about it. I'm going to erase this real quick. Another way you could actually think about it, which I kind of prefer, because it's a bit more all-encompassing, but it could be a little confusing for some students. So I prefer H3A 2+, H2A+, HA neutral, and also A-. And this actually goes perfectly with our formal charges that we attributed. And the A is just the product. I mean, it's just our molecule of interest. Like, this could have been any other amino acid that has 3 pKa's. So I'm actually going to notate everything in this way. So at our first pKa, which is the point at which we have a perfect buffer, essentially. Our pKa is where we have our perfect buffer. So at a perfect buffer, the Henderson-Hasselbalch equation tells us that pH is equal to pKa plus the log of base divided by acid. And of course, when it's a perfect buffer, our conjugate base and acid are going to be in the same concentration. We'll have the ratio should be 1 to 1. And if our ratio is in fact 1 to 1, this ratio over here would be 1. And what's the log of 1? The log of 1 is 0. Right, so it would end up being the pH is equal to the pKa plus 0, which equals pH is equal to pKa. Okay, so this fact is very important, because we know that at our perfect buffer at least, our slope is going to be as horizontal as possible, because it's having the least change in pH at that point, right? So they should all be horizontal this way. Okay, so I'm going to draw in our first pKa point. Our first pH point is our first pKa. So I'm going to draw that at 2.2. So if this is like 3.5, half between, so let's go around right here. 2.2. This is going to be our first point right here. Okay, let's go ahead and draw in our second point. Our second point is going to be 9, a pKa of 9, which should be around here, right there. That should also be a horizontal line, because our graph's going to look like this, right? So that's going to be our straight line portion of it. Straight line like that. And then at 10 is our last pKa. So where's 10? 10 is going to be somewhere around right here. Let's draw a straighter line than that. There we go, 10. And now let's go ahead and just connect these dots. It's going to start off like this. It's going to start off right here. It's going to go up this equivalence point, straight across again, up this equivalence point, and straight across again. Right? Okay, perfect. Now, let's go ahead and see if we can understand the rest of these questions. So sketch a titration curve for lysine. We went ahead and sketched that. Draw the primary species of lysine in each buffering region and equivalence points. So at the equivalence points, between, for example, 2.2 and 9, all we have is this at the exact equivalent point for our first equivalence point. And at the buffering region, all we have is these two, right, for our first one. So in this region over here, in this buffering region right here, all we have is these two amino acids. In this buffering region, all we have is these two acids. And in this buffering region right here, all we have is these amino acids. Right? So that's a good start right there. And then for the next question, define buffering region. How could you locate it on a titration curve? Well, the buffering region is going to be the region that experiences the least change in pH, right? And there's a mathematical way you could actually explain that, which I can go over right now, but these are obviously just rough circles. These green circles are just rough regions of the buffering region. But the general rule is your buffering region is equal to plus or minus 1 of your pKa. Plus or minus 1 of your pKa. So in this case, let me erase these green circles. In this case, let me add orange. It would be 3.2 and 1.2. So if these are in fact real, it would be this region right here. That entire region. For 7, oh no, not for 7, sorry about that. For 9, which is our point right here, 9, and then 10. For 9, it would be 8, 8, and 10, right? So it would be 8 and 10, so all the way to here. This would be our buffer region. And then for the last one, between 10, it would be 9 to 11. So 11 would be somewhere like right there. So all the way up to here. This would be our buffer region. And in this case, our buffer region, obviously they overlap for our second and third pKa. So our buffer region really is 8 to 11. It's from 8 all the way to 11 for our second buffer region. So we really only have 2 buffer regions, but you can also think about it as 3. Doesn't really matter. Okay? And define equivalence point and figure out how could you locate it on a titration curve. Well, the equivalence point is always going to be the point at which you have the most steep line, right? That is the most rapid change in pH because you've essentially used up all of your previous acid and now you've moved on to your second form, the second acid or the previous conjugate base in the case of amphoteric substances. And again, we're going to be dealing with amino acids in biochem right now, so they're all going to be amphoteric after the first pKa. And at the second pKa, in the case of 3 pKas. Okay, so I hope this helped. Sorry, a couple parts are pretty confusing, but I'll probably make another video soon with a better explanation. But this is pretty on the go. I'll plan out my next one. Yeah, these videos are honestly not just for you guys, but it's also for me. This helps me out a lot. I learn a lot as I do these. And the parts where I stumble, I obviously learn that I don't understand those parts well enough, and I have to go back and understand them more clearly. Einstein actually had a good quote once. He said that if you can't explain something in simple terms, you don't know it well enough. And that's kind of how I feel in making these videos sometimes. If I ever stumble, or if I make things longer than it has to be, if I overrun a topic, it's because I just don't understand it well enough, and I have to work on that. So thank you guys for watching, and have a great day.